Hello students, so today we are going to discuss about nucleation in a solution. Now the basic reaction or the basic relation explaining the nucleation in a solution is given as J, which is a nucleation rate, which has got units numbers per second per meter cube is equal to K0 exponential minus delta G star divided by KBT. Well, K0 is the kinetic factor, has got units per meter cube per second. Delta G star is the activation free energy expressed in joules, and whereas Kb is the Boltzmann's constant and T is the temperature. Now there are two usual methods of nucleation, rate determination. The first method, it consists of establishing supersaturation and measuring the time the crystal takes to become observable, and that is called the induction time. Now, if we plot the inverse of the induction time as a function of the square of log of the supersaturation, it will give the interfacial energy, that is gamma, and the kinetic factor, and the supersaturation range over which the experiments can be performed is limited to the metastable zone. So let us look at the plot. So this is a plot between the nucleation rate and supersaturation, that is beta. So you can see a clear demarcation of the metastable region and the spontaneous nucleation that takes place. So there has to be a certain period which has to be crossed for the spontaneous nucleation to take place. Before that, it is all the metastable region. Now when this beta, which is the supersaturation, is too small, then the heterogeneous nucleation may replace the homogeneous nucleation. So you can look in the YouTube 310 to find out about the heterogeneous and homogeneous nucleation. Now when beta is too large, the induction times are difficult to measure, and because they are too short. This was about the first method. If we come to the second method, then it is a direct determination of the steady state rate of homogeneous nucleation takes place here. And now at start, we start a temperature at which there is no nucleation, that is, the nucleation is prevented at that temperature. Now from that temperature, the temperature is lowered to a certain temperature T1, where the nucleation starts to occur. Now it is being held at T1 for a certain time, that is delta T1, and again the temperature is raised to a certain temperature T2, where the growth of the small nucleation embryo starts to take place. Now at T2, the supersaturation is at a level where the nucleation rate is practically zero. So there is no nucleation taking place. However, the growth continues, but the crystallites are already formed, can grow to a detectable dimension. So we see the plot of the concentration versus the temperature. So you can see that there are two lines. This is the metastable zone that we have mentioned previously, and this is the solubility curve. So initially, as stated, initially we are at a temperature where there is no nucleation taking place. So from that temperature, we come back to a certain temperature. We reduce the temperature where the nucleation starts to occur, that is the T1. So this is the first step, reducing the temperature to a lower temperature. Now again from that temperature, now it is being held at certain time. So if you look at the temperature versus time diagram. So this is from a certain temperature, it is brought back to a temperature where the liquefaction starts to take place, and now it is being held for a certain time delta T1 here. And after it has been held, that means this time is given for the formation of the small crystallites. And after all the small crystallites are formed after a certain time T1, the temperature is again raised. So from here, the lower temperature is again raised, but it is not crossing the solubility curve. So you can see that this is the temperature which has been raised to a certain temperature T2, and this is where the growth of crystallites takes place. And this is the second type of nucleation, rate accumulation.